I hope you have written exam in a very good manner. I hope so, right? Okay. So for electrical students, right? So in this analog electronics subject, they have given 5 questions here. Okay. So since we don't have the exact question paper available, right? So we have collected these 5 questions from the students who have written the GATE exam. So these questions are based on the memory of the students. So that's why I am calling them as memory based questions. Okay, memory based questions, right? So based on the data that we got, based on that we are going to deal with these 5 questions here, right? Okay. So let us start. I think for electrical students, whatever the questions they got in analog electronics, all are very simple questions. Only one question is typical. So remaining all the questions are very simple, right? Okay. Okay. Yeah. So let us start the first question, right? So write down the first question here. So the first question is the output impedance. The impedance of non-ideal non-ideal op-amp is denoted by Z out. The variation in magnitude of Z out with increasing frequency f in the circuit shown below. Okay, in variation in magnitude of Z out with increasing frequency f in the circuit shown below is best represented as represented as. Okay, so here they have given the circuit. So this is the circuit they have given. So they have given a voltage follower circuit here, or we can call this this voltage follower circuit is going to act like what? It is going to act like a buffer, right? Okay, right. So here we are having V in, this is grounded, and here we are having this negative feedback. So here this is output voltage. So they are asking about the Z out here, right? So what happens to Z out as the frequency increases? That means they are asking the frequency response. They are asking the frequency response of Z out. So how this Z out is going to vary with respect to frequency? So that we can call it as frequency response of what? Z out. So this is what we have to determine. So they have given some graphs here in option A, B and C and D. They have given some options. So out of those options, you have to choose the correct option. So option A they have given as, see, this is a Z out versus what? Versus frequency. So they have given in this manner option A. Option B they have given some constant like this Z out. Next, option C, they have given this. Okay, and option D, option D, they have given something like this, right? Okay, so among this you have to choose the right option here, right? Okay, so here just we have to determine for this circuit here, for the given circuit, you have to determine the frequency response of the output impedance. That's it, right? This is the question they have given. So the output impedance of a non-ideal here, they have given non-ideal op amp is denoted by Z out. The variation in magnitude of Z out with increasing frequency is can be best represented as for this circuit. Okay, for this circuit you have to get the frequency response of Z out here. Okay, okay, so the given circuit is nothing but voltage follower circuit, we know that one, right? So this is the given circuit, so this is minus and this is plus, and here this is Vn and this is the voltage follower circuit, this is V out. Okay, so we have to determine this Z out here, right? Okay. So now see here, see without feedback here, without feedback the gain of the op amp I am representing as what? I am representing as AOL. So this is the open loop gain, open loop gain. Okay, so with the feedback, what is the gain you are going to get? So the gain is nothing but AOL by what? By 1 plus A beta. Yes or no? So once you given the negative feedback here, this is negative feedback you have given. So in case of negative feedback, what will happen? The feedback gain of the amplifier will become what? Will be reduced, will become lesser than what? Will become lesser than the open loop gain. So this is the expression we are going to get. So because of the negative feedback, there will be a change in input impedance and also there will be a change in output impedance. Okay, so we try to analyze what happens to the input impedance and what happens to the output impedance in this case here, in this case. So first of all we have to identify the topology of this feedback, okay, okay. So how we can identify that? See here, see, if you are having an amplifier here, okay, so whenever you are giving the feedback, what you are going to do at the output, what you are going to do, you are going to sample. Yes or no? You are going to do sampling at the output, right? And at the input, what you are going to do, you are going to mix. Yes or no? Whatever the signal that you have sampled at the output, that you are going to mix at the input. So at the output, what is the operation you are doing? Sampling. And at the input, what you are doing? You are mixing, right? Okay, so you can sample the voltage at output here, voltage at output. So if you want to sample the voltage at output, so then at the output you have to sample through what? You are going to have shunt connection, right? And if you want to sample the current at the output, then you must connect at the output series. So you have to take the take the feedback from the output through what? Through series. See, that is, it is just like a, so this is amplifier, right? Okay, so here this is input side and this is output side, right? So output, you are sampling the voltage. If you want to sample the voltage, you have to take the voltage here like this, right? So this is called as uh, sampling the voltage. That means you have to connect in shunt here, right? Okay, okay. And if you want to if you want to sample the current, then what you have to do? If you want to sample the current, in that case how you have to connect? See here. So I am talking about the output here. Okay, at the output I am talking. So if you want to sample the current, what you are going to do? You are going to connect like this. Yes or no? Here you are going to have the output. Here it is output, right? Okay. So you are going to connect at the output in this manner. So this is called as a you are connecting in series here. You are connecting here. It is in series. So this is shunt connection, right? And here this is what? This is series connection. This is series connection. So in shunt you are sampling what? You are sampling the voltage. You are sampling the voltage. So in series connection you are sampling what? You are sampling the current. You are sampling the current. Okay. Okay. So similarly at the input, you are going to mix the signal. Whatever the signal that you have sampled at the output, that signal you are going to mix with the input signal at the input here, right? Okay. So at the input, see here, at the input, so if I consider at the input, so this is the amplifier, right? Okay. So at the input, so here this is a V in, and here you are going to have what? Source voltage, right? Okay. So if you want to mix, if you want to mix if you want to mix here at the input, what you are doing? You are mixing what? You are mixing the feedback voltage, whatever the voltage that you have taken or sampled from the output, that you are going to take, that is going to pass through the feedback network. Here you are going to have some feedback network. It is going to pass through the feedback network, and whatever the output of the feedback network, that you are going to mix at what? You are going to mix at the input. Okay. Okay, yeah. Right. If suppose you are mixing the voltage, let us say you are mixing the voltage here. Okay, you have to mix the voltage in this manner. Yeah, right? So that means here sorry, here you have to get here plus sign, and here it is minus sign, right? Okay, so here V in is equivalent to what? Minus to plus is V in, okay, minus Vs plus Vf is equal to 0 if I apply KVL around this loop, right? So then what you are going to get? V in is equivalent to Vs minus Vf, right? So you are mixing the feedback voltage, whatever the voltage that you got here, feedback voltage. Okay, this voltage you are mixing at the input. So whenever you are mixing the voltage, what is the connection you have done? This is nothing but series connection. So in order to mix the voltage, what you have to do? You have to connect in series. So similarly, if you want to mix the current here, then you have to connect at the input in shunt here. So at the input, okay, so this is the input, and we have to connect it in shunt. Okay, so this is shunt connection, right? So here you are going to what? You are going to mix current, mixing current, right? Okay, so this is what you have to understand about the feedback here, right? So whenever you are mixing the voltage, what must be the connection at the input? It must be what? It must be series connection, right? If you want to mix the current, what must be the connection at the input here? It must be what? It must be shunt, right? Okay. Okay, now in our question here, what we are doing? So here at the output, we are taking a part of the voltage from the output. That means you are sampling the voltage. Here you are sampling voltage. Okay, so that means at the output you are going to have what? You are going to have shunt connection, right? Okay, and whatever the voltage that you have sampled here, that is fed back through this feedback network. This is the feedback network, and it is mixed at the input here. It is mixed with the input signal here. Understood? Okay, so here mixing is also what? Here mixing is also voltage. Mixing is also voltage. So if you mix the voltage, then the connection is nothing but what? Series. Understood? Okay, so generally we call this as what here? We can call this as series shunt connection. We can call this as series shunt connection. At the input it is series, at the output it is shunt. So we can call this as a series shunt connection. So at the output we are sampling the voltage, and at the input also we are mixing the voltage. So this is a series shunt connection, or we can call it as what? At the output what you are sampling the voltage. Yes or no? So we can call this as voltage, and at the input what is the connection? Is nothing but series. So we can call this also as a voltage series connection, right? We can call it as series shunt, or we can call it as voltage series feedback, right? So the given circuit, represents what here? Represents we can say either series shunt, or first you are going to represent here. First you are going to represent whatever that you are sampling. So which signal you are sampling? You are sampling at the output, you are sampling voltage. So first we will write voltage, and at the input what is the connection? Series. So we can call it as what? Voltage series feedback also. So series shunt feedback, or we can call it as voltage series feedback, right? Okay, so in case of voltage series feedback here, in case of voltage series feedback, at the input you are mixing voltage, and at the output you are sampling what? Sampling voltage. Understood? So here the type of amplifier you are going to get is nothing but what? Is nothing but a voltage amplifier. Is nothing but voltage amplifier. Understood? Okay, okay, yeah. So whenever you give this feedback here, so what happens here? At the input, that is Zin is going to increase. Right? Whenever you give the feedback, the input impedance is going to increase here. Whenever you give the negative feedback here in voltage series connection, okay, the input impedance is going to increase. And how much it is going to increase? It is going to increase by a factor of 1 plus a beta. Okay, so Zin with feedback is equivalent to what? Is equivalent to Zin into 1 plus a beta. So Zin with open loop, right? The input impedance with open loop into what? Into 1 plus a beta. So that means the overall input impedance in feedback is going to increase by what? Is going to increase by 1 plus a beta factor. Understood? Okay, and similarly the output impedance is going to what? Is going to decrease. See, whenever you are having the negative feedback in case of voltage amplifier, the input impedance is going to increase, the input impedance is going to increase, and the output impedance is going to decrease by a factor of what? By a factor of 1 plus a beta. So this is the output impedance with feedback network here. Understood? Okay, so now see here. So the output impedance with feedback. So therefore the output impedance with feedback here we got what? We got ZOL by what? By 1 plus a beta. So now we have to analyze what happens to this output impedance with respect to what? With respect to frequency. So for that what we are going to do here is this beta is nothing but what? Is nothing but feedback factor. This beta is nothing but feedback factor. So here we are having a voltage follower. Yes or no? Voltage follower like this, right? Voltage follower circuit, right? So what is the feedback factor for this one here? Beta is equivalent to, so here this voltage, so the feedback voltage here is same as what? Is same as this input voltage. So the feedback factor, you are going to get what? You are going to get 1 here. Yes or no? So the feedback voltage is same as what? Is same as the input voltage here. This voltage and this voltage is same. So you are going to get the feedback factor as what? As 1, right? Okay. So the feedback factor is 1. So here remember, this A is nothing but what? This A is nothing but open loop gain here. Open loop gain. So here this A is nothing but open loop gain, right? Okay. Okay. So here, so for the given circuit, for the given voltage follower circuit, for the given circuit, beta feedback factor beta equal to 1. So therefore I can write ZOF, that is output impedance with feedback, is equivalent to what? Is equivalent to ZOL by what? By 1 plus AOL, where AOL is nothing but what? Is nothing but open loop gain, right? Okay. And here they have given non-ideal amplifier here. They have given non-ideal amplifier. So they have given non-ideal op-amp. Yes or no? Non-ideal op-amp. So for this non-ideal op-amp, what is the frequency response you are going to get here? Frequency response. So that is a gain versus frequency. Gain versus frequency. Okay. So whenever this op-amp is in open loop. Okay. So open loop gain versus frequency. So how it is going to look like? So we know that the op-amp is going to act like what? It is going to give you low pass filter frequency response here. It is going to give you low pass filter frequency response. So here, if you know the frequency response of a non-ideal op-amp, then it is going to be very simple. So here it is F and here it is AOL. So the frequency response will be like what? Will be like low pass, right? And they have given it is a non-ideal. So non-ideal op-amp means so the frequency response will be what? Will be like this. It is going to decrease like this. Yes or no? So ideal means what here? Ideal means you are going to get the frequency response like this, right? Okay. But here they have given non-ideal op-amp. So the gain is not going to decrease suddenly in this manner, right? Suddenly in this manner. So it is going to fall off like this. Okay. Okay. Yeah. Okay. So this is open loop gain versus frequency, right? Okay. So wait. So this is what? This is some 3 dB cutoff frequency, right? Okay. Okay, so this is the frequency response of an op-amp. This is the frequency response of an op-amp. That is a open loop gain versus frequency here, right? So now if you observe here, as the frequency goes on increases, what is happening? So initially the open loop gain is constant. From here to here, open loop gain is constant, and from here it starts what? It starts falling, right? Okay. So that means up to some frequency, let us say f1. Okay, up to some frequency the gain is constant. After f1, what will happen? The gain is decreasing, and finally as f tends to infinity, this will become what? This will become 0. So that is the frequency response of AOL. Now if I try to draw the frequency response of ZOF, what you are going to get? See here, AOL is constant up to what? Up to f1. Then up to f1. Then for f greater than f1, this AOL is going to what? Is going to decrease. So whenever this AOL is constant, this ZOF value is also going to be constant. Yes or no? Then after f1 frequency, after F1 frequency, this AOL will starts decreasing. So if this AOL starts decreasing, then this denominator term is going to decrease, which means the output impedance is going to increase. Okay, so at one stage what will happen? AOL will go to what? Will go to 0. So whenever AOL becomes 0, ZOF will become equivalent to what? ZOL. So that is the maximum output voltage you are going to have, right? Okay, so now I can draw output voltage with respect to what? With respect to frequency, right? So output voltage with respect to frequency. So this is frequency, and this is, sorry, output impedance with respect to what? With respect to frequency, right? Okay, okay, yeah. So ZOF is equivalent to what? Is equivalent to ZOL by 1 plus AOL, right? Okay, so up to F1 frequency, AOL is constant, so ZOF is also constant here. Up to some frequency, ZOF is also constant. Then after F greater than F1, AOL is what? So in this region AOL is constant, right? And here in this region AOL starts what? Starts decreasing. So if AOL starts decreasing, this denominator term is going to decrease. So ZOF is going to what? Is going to increase. Right? So let us assume at certain frequency, at some frequency, right? At this frequency F2, let us say this frequency F2. Let us assume at frequency F2, AOL is becoming equal to 0. At frequency F2, AOL is becoming equal to 0. So if AOL becomes 0, then ZOF is equivalent to what? ZOL. So it reaches to this frequency here. Okay, then AOL will be what? AOL will be 0. After this frequency, AOL will be 0. So that means ZOF will be maintained at ZOL. So this is going to be ZOL, right? So it is going to start at some value here, and then it is going to increase, and then it will become constant after frequency F2, right? So this is the frequency response you are going to get with respect to what? With respect to output impedance, right? So this is output impedance versus what? Versus frequency. So this is the frequency response here. Okay, so output impedance, frequency response. So this is the correct answer. So let us check which graph is correct. Let us check which graph is correct. So initially it must be some constant, and then it has to increase, and then again it has to become constant. So option C is correct here. So option C is correct for this question. Option C is correct for this question. Okay, this is the right answer here, right? Okay, so only this is the question which is somewhat typical here, right? Remaining all the 4 questions are very simple. Only this question is somewhat typical for electrical students. Remaining all the other 4 questions are very simple. Okay, okay. So now let us take the second question. Let us take the second question. Right? So what they have given here is for an ideal MOSFET, 1 minute here. So some muscle catch in the leg. Okay, so next question, write down for an ideal MOSFET, biased in saturation, the magnitude of the magnitude of small signal current gain, for a common drain amplifier, is. So it is a direct and simple question here. So option A they have given as 1, option B they have given 100, option C they have given 0, option D they have given infinity. Okay, see they are just asking the current gain for what? For common drain amplifier. So for an ideal MOSFET biased in saturation region, it is biased in saturation region, the magnitude of a small signal current gain for common drain amplifier. We know that for common drain amplifier here, for common drain amplifier, we know that the voltage gain will be equal to what? Will be equal to 1. It is approximately equal to 1, right? Voltage gain will be 1. So what is current gain here? What is current gain? So in case of common drain, input is nothing but what? Input is nothing but a gate terminal. Input is given at gate and output is taken at what? Output is taken at source, right? Okay, so at the input, what is the current here? The input current will become what? Since you are giving the input at gate, the input current will become IC and the output current will become what? Will become source current, right? Okay, okay, yeah. So now, right? Okay, so now what is the small signal current gain here? So small signal current gain is equivalent to what? Is equivalent to change in output current, so that is delta is divided by what? Delta ig. Okay, so what is the change in delta is? We don't know that, so let us say delta is divided by what is the change in Iz here? So Iz is equivalent to what? Iz is not going to change here. Iz is always what? Iz is always 0 amperes. Yes or no? Okay, so in MOSFET Iz will be always equal to what? 0. So delta Iz will be equal to what? Will be equal to 0. So that means the current gain, small signal current gain, you are going to get what? You are going to get infinity. Whereas a small signal voltage gain will be approximately 1 and the current gain will be what? Will be infinity for what? For common drain amplifier. So the correct option for this question is option D. Okay, so it is very direct and simple question here, right? So there will be no change here, there will be no flow of current at all through the gate. Understood? So that's why always Iz will be equal to 0, always, whether it is a DC or AC, always Iz will be equal to what? Iz will be equal to 0. There will be no change in Ic, it will be always equal to 0. Understood? Okay, okay. So that's why small signal current gain, you are going to get what? You are going to get infinity. So this is very simple problem. I hope you can easily understand this one, right? Okay, okay. So we have completed 2 questions and next the third question. Write down the third question here. So here they have given an op-amp circuit like this. So this is the op-amp circuit. Here they have given 0.1 volt. Okay, and here this is R1. Here this is operational amplifier, this is minus, this is plus, and here you are having R2, and here you are having a minus VEE, and here having VCC, right? And here they have given the capacitor. Here they have given the capacitor, and this is the output V out. Okay, okay. So just by seeing this circuit, we can say that it is acting like what? It is acting like a integrator circuit. Okay, so it is acting like a inverting integrator here, inverting integrator. Understood? Okay, okay, yeah. So they are asking here V out, they are asking here V out for this circuit, right? Okay, so we know that what is V out here, what is V out for this circuit here. See here, this is V out, and since you are having here negative feedback through this capacitor voltage, so here we can apply what, we can apply virtual short concept. So that is here it is 0 volts, and here also what, here also it is 0 volts. So here the current flowing here the current flowing is I1, let us say, right? And here the current flowing is nothing but IC. Okay, okay, yeah. So now this I1 must be equivalent to what, IC, because the current through the to the input of the op amp is always equivalent to what, 0 ampere. Op amp doesn't draw any input current. Okay, so this I1 must be equal to IC, right? So I1 must be equivalent to IC. So I1 is nothing but what, I1 is nothing but 0.1 volt minus 0 divided by what, divided by R1. So this is equivalent to, this is equivalent to IC. What is IC here? IC is nothing but C into d by dt multiplied by, here you have to write the voltage across the capacitor. What is the voltage across the capacitor? Here you are having 0 volts, and here you are having V out. Okay, so plus minus Vc. So Vc is equivalent to what, 0 minus V out here. So that is 0 minus V out, that is V naught I am representing, V out or V naught. Okay, okay. So now what you are going to get? Okay, what you are going to get here? So here V out, so this is V out. Okay, okay. So here you are getting 0.1 divided by R1. So I am integrating on both sides here. If I integrate with respect to time on both sides, what you are going to get? You are going to get here minus C into V out. Okay, okay. So therefore, so I have integrated on both sides, we got this expression. So therefore V out is equivalent to what, is equivalent to minus R1 into C into integral 0.1 into t. So this is what 0.1 into dt here, 0.1 into dt. So this is what you are going to get, right? So if you do this, what you are going to get, minus 0.1 integral dt is nothing but t, 0.1 into t divided by what, divided by R1 into C. So this is the output voltage you are going to get. Okay, okay. So now see here, this is the output voltage you are going to get. This is the output voltage you are going to get, right? So input, what you have given, input you have given 0.1 volts, that is DC signal you have given. Yes or no? So this 0.1 is nothing but what, 0.1 is nothing but V in. This is the input voltage you have given. So integration of V in dt into minus 1 by RC is nothing but what, is nothing but V out, right? So output is equivalent to some constant multiplied by what, multiplied by integration of the input voltage. So if input is constant here, if input is DC, if input is DC or constant, then output will become what, output will become a ramp function or not. The integration of constant function is nothing but what, is nothing but ramp function. Understood? Now here this is a increasing ramp or decreasing ramp here. So it depends upon the slope of this ramp function. So this represents the slope here. So since this is a negative slope, here you are having negative slope, so you are going to get a decreasing ramp, you are going to get decreasing ramp function at the output, right? So if I draw the output here with respect to time, then what you are going to get? So here V out with respect to what, with respect to time, right? When t equal to 0, V out is equivalent to what, V out is equivalent to 0, right? So as t goes on increases, this slope, sorry, this slope will be what? This slope is negative here. This slope is negative and constant. So that means you are going to get a ramp which is decreasing like this. So you are going to get a negative ramp here. You are going to get negative ramp. Understood? So that means V out will goes on what? Will goes on decreases. Will goes on decreases. But up to what value it can decrease here? It can decrease up to what? Up to minus V sat here. It can decrease up to minus V sat. So here minus V sat is equivalent to what? Is equivalent to minus VEE. So it can decrease up to minus VEE. So once it tries to go beyond minus VEE, what will happen? The output voltage will be saturated at what? Will be saturated at minus VEE. It cannot go up to minus infinity, yes or no? So it will go up to what? Go up to minus V sat. So after that, what will happen? It will stay at what? It will stay at minus V sat. It continues to stay at what? Minus V sat. That is minus VEE, right? Okay, okay. So now if they have asked the output voltage at t equal to infinity here, that means as t tends to infinity, the output voltage what? As t tends to infinity, the output voltage will be equivalent to what? Will be equivalent to minus VE. Okay, they have simply asked output voltage. Okay, we don't know whether they have asked for t equal to infinity, or they would have given some t value here. If they would have given some t value like 0.1 millisecond or something like that, okay, then you have to substitute that value in V out expression and you have to get the output voltage. Understood? Okay, we don't have any data whether they have asked for t tends to infinity or for any particular value of t. We don't know that one, right? Okay, okay, yeah. So this is the general representation of the output. This is the general representation of the output output voltage. So this is the general representation of the output voltage. Understood? So if t is very large here, if t is very large, that is as t tends to infinity, this V out will reach us to what? Will reach us to minus VE. Or if you know t value, if they have given any t value, then at that t value you can determine what? At that t value, and if they have given R1 value and C value, so if you substitute these values, you are going to get the particular output voltage. Understood? Okay, okay. So it all depends upon what they have given in the question here, right? So since we don't have that information whether they have asked for t tends to infinity or at any particular t value, right? If they would have asked for t tends to infinity, then the answer must be what? Then the answer must be minus VE, right? Okay, okay. So this question is also completed. So we have completed how many questions here? We have completed, I think, 3 questions, right? So next, we'll write down 4th question here. Write down the 4th question. So what they have given here is the current gain. The current gain I out by I in. I out by I in the circuit. In the circuit with an ideal current amplifier, with an ideal current amplifier given below. Okay, so here they have given options: A minus CC by CF, option B minus CF by CC, option C CC by CF, option D CF by CC. So here they have given the circuit here. I am drawing the circuit. So for that circuit, you have to determine what? You have to determine the current gain, that is I out by I in, right? So here this is the circuit they have given. So here this is I in. This is off amp, and here this is minus, this is plus, and it is grounded here. and here they have given one capacitor, and here they have given another capacitor, and here it is grounded. Here they have given the current as I out, and here this capacitor they have given as CF, and this capacitance they have named as CC. So for this circuit you have to determine what? You have to determine I out by I in, I out by I in. So how we can determine this? How we can determine this? See here, see, it is very simple here. See, I don't know the voltage here. I don't know the voltage here. So this voltage I am representing as VA. Okay, I am representing this as VA. Right? Okay. So here, since you are having here negative feedback, we can apply what? We can apply a the virtual ground concept. So here it is 0 volts. So here also it must be what? It must be 0 volts. And here they have given in is flowing, in is flowing like this, in is flowing like this, and here op amp cannot draw any current, so the current through the op amp is 0 amperes. So what must be the current that has to flow here? Tell me. So if you apply the KCL, what you are going to get? So here the current leaving is in, here it is 0 amperes. So what must be the current that has to flow here? That has to flow here is also nothing but what? Is also nothing but in. Yes or no? Is also nothing but in, right? So therefore in is equivalent to what? In is equivalent to, I can write it as what is the expression for in? So this in is the current through the capacitor CF. So that is CF into what? CF into d by dt into voltage across the capacitor. So here you are having VA and here you are having the voltage 0. So since the current is flowing like this, you have to consider the voltage as what? Voltage across the capacitor as VA minus what? VA minus 0. So this is equivalent to CF into dVA by what? dVA by dt. So this is in here. This is in. Okay. So this is in. So therefore in is equivalent to CF into dVA by dt. dVA by dt. dVA by dt. Okay. Okay. Now see here. I out here. What is I out here? What is I out? I out is also the current through what? Current through capacitor CC. The current through capacitor CC. So here I can write I out is equivalent to what? I out is equivalent to CC into what? I out is equivalent to CC into d by dt. d by dt into what? Into, so the voltage across the capacitor, that is VA minus what? Here it is nothing but what? 0 volts. So VA minus 0. So VA minus 0. So what you are getting? CC into what? Into dVA by what? dVA by dt. Okay. So I out is equivalent to CC into dVA by dt. That's what we got. Okay. So I out is equivalent to CC into dVA by what? dVA by dt. This is I out. Okay. So let us say this is equation 1 and this is equation 2. So from these two equations, what is I out by 1 minute here. So I think now you can see I out, right? So I out is equivalent to what? Is equivalent to CC into dVA by dt. Yes or no? So this is I out here. Here the current flowing is I out. So I out is equal to CC into d by dt of voltage drop across the capacitor, that is VA minus 0. Okay. So you are going to get CC into dVA by dt. Right? Okay. So now it is very simple here. If you take the ratio of I out to I in, so this dVA by dt will get cancelled. So therefore you are going to get what? I out by I in. I out by In is equivalent to what? You are going to get a Cc by what? Cc by Cf. So this is the answer you are going to get, I out by In, right? Or if you want, you can do the same question in another manner. So that is, this is very simple procedure here. So you can do, if you want, I out is what? I out is the current through what? Current through capacitor Cc, current through capacitor Cc, and the voltage drop across the capacitor Cc is nothing but what? Is nothing but Va. So I can write Va is equivalent to what? Va is equivalent to 1 by Cc into integral I out into what? Into dt. In this manner also I can represent. Understood? So therefore I can represent In is equivalent to Cf into what? Cf into dVA by dt. So that is d by dt, and Va is nothing but what? 1 by Cc into integral I out into what? Into dt. So here we are doing integration with respect to what? Integration with respect to time, and integration with respect to time, and differentiation with respect to time. So this differentiation, this integration will get what? Will get cancelled. So what you are going to get? In is equivalent to Cf by Cc into I out. Okay, In equivalent to Cf by Cc into out, Cc into I out. So therefore I out by In. So I out by In, what you are going to get? You are going to get Cc by what? Cc by Cf. The same result you are getting. Okay. So in either manner you can solve here, right? Okay. So for this question, the answer is nothing but what? The answer is nothing but Cc by Cf. So let us see which option is correct. So that is option C. So option C is correct for this question, Cc by Cf, right? Okay. Okay. Yeah. So 4 questions done. So last question here, last question for electrical students. Okay. So last question here. So 5th question. So this question is a diode circuit here. This question is given based on diode circuit. So what they have given here is for the circuit shown below, for the circuit shown below with ideal diodes, with ideal diodes, the output will be okay. So here they have given the circuit. So this is diode D1, and here they have given another diode, so which is diode D2. Okay, and here this is nothing but what? This is nothing but R, and here this is V out, and here they have given V in, which is sinusoidal, some sinusoidal signal like this. Understood? Okay. So here options for this circuit, they have given the options. They have given the options. Option A, V out is equivalent to V in for V in greater than 0. Option B, they have given V out equal to V in for V in less than 0. Option C, V out equal to minus V in for V in greater than 0. Option D, V out equal to minus V in for all V in. Okay, so this is what they have given the options here. So you can easily analyze this circuit here. This is very simple circuit. Yes or no? Okay. Okay. So see here. See, during positive half cycle here. During positive half cycle. Right, during positive half cycle, which diodes will go to on and which diodes are going to be reverse biased here? Which diodes are going to be on and which diodes are going to be off? So during positive half cycle, we can easily say that it will try to pump the current in clockwise direction. Yes or no? Okay, so D1 is going to allow. So always diodes will allow the current from where to where, from P to N. So here also this is P side, this is P2 and this is N2 and this is P1 and this is N1, right? Okay, so during positive half cycle the current will try to flow in clockwise direction. So which means I can say simply D1 will be what? D1 will go to on state and D2 will also go to on state. See, remember, once the closed path forms here, then only the current is going to flow in this circuit. Okay, so during positive half cycle, D1 will go to what? Will go to on state and D2 will also go to on state, right? Why here? Because here N2 will be what? N2 will be at a lesser potential. During positive half cycle, N2 will be at lesser potential. So cathode is at lesser potential than what? Than the anode side. So that's why this diode will go to on state during positive half cycle. And during positive half cycle, this P1 is going to be at higher potential when compared to N1. So this diode D1 will also go to what? Will also go to on state, right? So whenever during positive half cycle both diode D1 and D2 will go to on state, so the circuit will looks like what? So for V in greater than 0, so D1 will go to on state and D2 also goes to what? On state, and the circuit will looks in this manner, right? Okay, so the circuit will look in this manner. So whatever that you are going to apply, so that is going to appear at the output. So V out is equivalent to V in here. V out is equivalent to V in for V in greater than 0. Next, for V in less than 0, what will happen? We will see. For V in less than 0 here, for V in less than 0, so I am taking another color. Let us take green. Okay, so for V in less than 0, okay, so here it is going to be at lesser potential. So this diode will go to what? Will go to off state, right? And here it is going to be at higher potential when compared to this one. So here this will go to what? So this will, here it is going to be at higher potential when compared to P2. So this diode will go to what? Will go to off state here. This diode will go to off state. So both the diodes will go to off state during negative half cycle. Understood? Okay, see, one thing you can remember, during negative half cycle this circuit will try to pump the current in anti-clockwise direction. So if it tries to pump the current in anti-clockwise direction, the current has to flow from N2 to P2 here, and here it has to flow from N1 to P1. But we know that diodes D1 and D2 are not going to allow the currents from N to P. So that means there will be no current flow during the negative half cycle here, right? So which means this D2 will be off and D1 will also be off state, right? So that means the input is completely disconnected with the output. Yes or no? So that means the output will be 0. There will be no current through the resistor. So the output will be at 0 for V in less than 0. So for V in less than 0, the circuit will become what? The circuit will be like this. So here it is open. Here you are going to have resistor. Here this diode is also open, right? So this is the circuit you are going to have. So since the current through the resistor is equal to 0, so this output will be equivalent to what? Will be equal to 0 for V in less than 0. So from this two, what we can conclude? We can conclude that V out equal to V in for what? For V in greater than 0, and V out equal to 0 for what? For V in less than 0. So these are the conclusions we can make. So from these conclusions, try to determine the answer, try to get the answer. So which option is correct here? Tell me. So option A, they have given V out is equivalent to V in. Option A, they have given V out equal to V in for V in greater than 0. So option A is what? Option A is correct. Next, see option B, what they have given? V out equal to V in for V in less than 0. For V in less than 0, V out must be what? Equal to 0. So option B is wrong. Next, in option C, they have given V out equal to minus V in for V in greater than 0. No, V out equal to V in we got. Yes or no for V in greater than 0. So option C is also wrong. And here they have given V out equal to minus V in for all V in. So this option is also wrong. So what is the right option for this question here? V out equal to V in for V in greater than 0. So during positive half cycle, both the diodes will start conducting, and during negative half cycle, both the diodes will go to half state. So the output will be like this here. So you are going to have during positive half cycle, you are going to get the output like this. Okay, and during negative half cycle the output will be 0. Again at during positive half cycle the output will be follow input and so on. So this is just like what? This is just like a half wave rectifier. So this circuit is acting like what here? This circuit is acting like a half wave rectifier circuit. Understood? Okay, so I hope all these things are crystal clear here, right? So with this, I am ending up this session, right? So I hope each and every question is crystal clear. Is crystal clear. So with this, I am ending up this session, right? Okay. So I hope you have understood each and every question, and uh, I hope you are going to get some good results in GATE examination, right? So thank you for watching. Thank you for watching Entry App. So take care, right? Okay. Okay. So in this session, so first of all of you, welcome to Entry App. Welcome to Entry App, and we are going to discuss here GATE 2022 electrical questions for EMT subject in EMT subject. Okay. So total they have given 3 questions in EMT subject here. So 2 questions are for 2 marks and 1 question is for 1 mark. So totally 5 marks they have given here. Totally 5 marks they have given for electrical. See, gradually the weightage for EMT is growing on for electrical students also, right? Okay. So for EC this year, they have asked only around 6 to 7 marks, 6 to 7 marks in EMT, whereas for electrical students they have asked for 5 marks. So the syllabus for electrical students is very less when compared to EC students, so they can easily score. If they would have studied this subject, then they would have easily scored this 5 marks. Understood? Okay. Okay. So I hope you all have written the exam in a very well manner, right? And I hope you are going to get some good results and some good ranks, right? Okay. Okay. So first we'll start the first question here. First question. So total 3 questions. So the first question I'm writing. One minute here. 1 minute. I'm checking the question. Okay. So what they have given is a vector field. A vector field E bar is equivalent to 2x ax cap plus 5y ay cap plus 3z az cap plus 3z az cap. Then find value of triple integral divergence of E bar into dv is where where V is the volume, where V is the volume enclosed by volume enclosed by unit cube, enclosed by unit cube, where x is ranging from 0 to 1, y is ranging from 0 to 1, and z is also ranging from 0 to 1. So this is the question they have given here. So you have to determine, you have to evaluate this triple integral divergence of E bar. That's it. Okay. Okay. So it is very simple and direct question. Yes or no? So they have given the vector field. So they have given some vector field E bar which is equivalent to 2x ax cap plus 5y ay cap plus 3z az cap. Right? Okay. Am I recording this or not? I'm getting doubt. 1 minute. Okay, I'm recording, no problem. Okay. Okay, so this is the vector field they have given, and they are asking us to determine the value of what? Triple integral divergence of E bar into dV, and where here V is the volume enclosed by what? Enclosed by a unit cube whose range x is varying from 0 to 1, y is varying from 0 to 1, and z is varying from 0 to 1. So it is very simple and direct question. So if you determine divergence of E bar, what you are going to get? Tell me. If you determine divergence of E bar, what you are going to get? So here the solution. Okay. So here this is the question here once. 1 minute. So this is the question they have given, right? A vector field E bar is equal to 2x ax cap plus 5y ay cap plus 3z az cap, right? So then you have to find the value of triple integral divergence of E bar, and they have given the range of x, range of y, and range of z. Okay. Okay, so what they have given? They have given E bar is equivalent to, they have given some vector field. So E bar is equivalent to 2x ax cap plus what? Plus 5y ay cap plus what? Plus 3z az cap. This is what they have given. So you have to evaluate triple integral divergence of E bar into dV. So what I am doing here is first I am going to evaluate divergence of E bar. So divergence of E bar is equivalent to. So here I am considering this is nothing but what? This is nothing but x component of vector field, and this is nothing but y component of the vector field, and this is nothing but z component of the vector field. Divergence of E bar means is nothing but what? Dou E x by dou x plus dou E y by dou y plus dou E z by dou z. Okay, so this Ex is nothing but what? 2x. Okay, so what is the differentiation of 2x? You are going to get 2 plus what is the differentiation of 5y? Is nothing but 5 plus what is the differentiation of Ez? Is nothing but what? That is the differentiation of 3z, that is nothing but 3. So what you are going to get? This is equivalent to 10. So this is the value of divergence of E bar. Now we evaluate a triple integral divergence of E bar dV. Okay, so therefore triple integral divergence of E bar into dV is equivalent to what? Here dV is nothing but what? Dx, dy, dz. These are the integration variables. So here you have to write the range of x, range of y, and range of z. So here x is varying from where to where? 0 to 1, and y is varying from where to where? 0 to 1, and z is also varying from 0 to what? 0 to 1. Divergence of E bar value is 10. So 10 into dV is nothing but dx dy into what? Dz. So if you substitute this, what you are going to get? 10 into what? 10 into x Okay, and if you substitute the range, what you are going to get? 1. So into y you are going to get, if you substitute the range 1 you are going to get, if you substitute the range for z you are going to get 1. So it is very simple integration here, you can easily solve this. So you are going to get what? Finally you are going to get 10 here, you are going to get 10. So the answer for this question is nothing but what? Is nothing but 10, right? Okay, okay. So the answer for this question is nothing but 10. So I have not given the options now, so there is no need to give the options here. If you want you can write the options. So they have given option A as 3, option B as 8, option C as 10, option D as what? 5. Okay, so what is the right answer here? Right answer is nothing but option C. Option C is the right answer, that is 10. Here it is not taking any other clue. Okay, okay, so this is the first question they have given. So we can easily answer 1 mark for this. We can easily get 1 mark for this question. Okay, okay. So next I'm writing the second question here. Second question. So write down the second question. Okay. So consider the magnetic field intensity. They have given the second question as a consider the magnetic field intensity. Magnetic field intensity H bar is equivalent to x square ax cap plus what? Plus x square y square ay cap plus what? Plus x square y square into z square az cap ampere per meter. Ampere per meter. Okay, x square ax cap plus x square y square ay cap plus x square y square z square az cap ampere per meter. So then they are asking the value of magnitude of z bar, at x equal to 1 meter comma y equal to 1 meter and z equal to 1 meter is. Okay, so this question is given for 2 marks here. This question is given for 2 marks. It is very simple question, so you can easily answer this one. Yes or no? Okay, so how you can solve this question? Tell me. 1 minute here. What happened? Okay, 1 minute. I'll refresh. Where is one note here? Where it is? Okay. Okay, so here I'm writing the second question here. First question completed. So the second question. So the second question what they have given here is consider consider magnetic field intensity. Consider magnetic field intensity. Magnetic field intensity H bar is equivalent to x square ax cap plus x square y square ay cap plus x square y square z square az cap ampere per meter. Okay, so they have given the magnetic field intensity and they are asking the value of magnitude of z bar at x equal to 1 meter, y equal to 1 meter and z equal to 1 meter. Okay, so at x equal to 1, y equal to 1 and z equal to 1, they are asking us to determine the value of what? The value of magnitude of z bar. So here they have given h bar here. Here they have given the magnetic field intensity, right? And they are asking us to determine the magnitude of z bar. So we know the relation between what? Between this h bar and this z bar from what? From Ampere's law. Yes or no? So we know that from Ampere's law. From Ampere's law. From Ampere's law, we know that curl of h bar is equivalent to what? Is equivalent to z bar. You want the magnitude of z bar means you have to determine magnitude of what? Curl of h bar. That's it. Okay. Okay. So now here I'm writing. So this is x square, right? So this is nothing but x component. So I am representing this with hx, and this x square y square is nothing but y component. So I am representing with hy, and x square y square z square is nothing but what? Is nothing but z component. So I am representing it with hz, right? Okay. Okay. So now I am so therefore here therefore magnitude of z bar is equivalent to what? Is equivalent to magnitude of what? Magnitude of curl of h bar. Okay, so that is equivalent to magnitude of what is curl of h bar here. I am expanding curl of h bar. So I have already told how to expand this one. So ax cap into dou by dou y minus dou by dou z plus ay cap into dou by dou z minus dou by dou x plus az cap into dou by dou x minus what? Minus dou by dou y, right? Okay, so here this is the magnitude. So here what you have to write? So here this is a h z, and here okay, so I'll take another color. Okay, so this is a h z, and here it must be hy, and here it is hx, and here it must be hz, and here it must be hy, and here it must be hx, right? So here hz is how much? Here is nothing but x square y square z square. Similarly hy is nothing but what? X square y square, and here hx is nothing but what? Hx is nothing but x square, and here hz is nothing but x square y square z square, and here hy is nothing but x square y square, and hx here is nothing but what? X square. Okay. Okay, so if you solve this one, what you are going to get? Tell me. Now it is very simple here. So this is equivalent to ax cap into, so I am considering magnitude ax cap into, so what is the differentiation of x square y square z square with respect to y here? Is nothing but 2y x square z square. Okay, and here you are differentiating this y component with respect to z. So here this y component is independent of z. So dou hy by dou z will become what? Will become 0. So this term will become 0. Right? So this is ax cap you are going to get plus ay cap plus ay cap into. So here dou by dou z and hx is nothing but what? X square. Okay, so hx is independent of z. So if you differentiate this hx with respect to z, you are going to get what? You are going to get 0 here. Next, hz is nothing but x square y square z square. So if you differentiate this x square y square z square with respect to what? With respect to x, what you are going to get? You are going to get 2x into y square z square, right? Plus what you are having? Az cap. So az cap into, so what is the differentiation of hy with respect to x? Hy is nothing but x square y square. So if you differentiate this with respect to x, you are going to get what? 2x y square. And hx is nothing but what? X square. So hx is a function of only x. Now here you are differentiating this hx with respect to y. So this term will become what? Will become 0. So this is what you are going to get, the magnitude of what? This is nothing but magnitude of curl of h bar. So they are asking this value at x equal to 1, y equal to 1 and z equal to 1, right? Okay, so therefore at x equal to 1, y equal to 1 and z equal to 1, magnitude of z bar is equivalent to, so what you are going to get is equivalent to magnitude of curl of h bar, which is equivalent to, you are going to get 2ax cap plus what? 2ay cap plus what? Plus 2az cap. So you have to determine its magnitude. So what is its magnitude? Is nothing but square root of what? Square root of 2 square plus 2 square plus 2 square. That is 4 plus 4 plus 4. That is square root of 12. So I can write this as 2 times of root 3. I can write this as 2 times of root 3. So if you find out 2 times of root 3, you will get, I think, 3.464, I think so. Okay, you will get like this here. So you can calculate this value to root 3, right? Okay. So I hope everybody, almost all the students have done this question, right? Okay, right. So it is directly based on Ampere's law. So the magnitude of z bar is how much here? Therefore, the magnitude of z bar is equivalent to what? Is equivalent to 3.464 ampere per meter square. Right? Okay. For electrical students, they have not given any MSQ questions here. Right? Okay. Next, last question in EMT. So that is a third question here. Let us take the third question. So what they have given here is a long conducting, a long conducting cylindrical wire, long conducting cylindrical wire of radius b is placed on z axis, and z bar is given as, z bar equal to, they have given it as z suffix a into r power 5, sorry, r power 3. This is, they have given as r power 3, r power 3 az cap, for r less than b. R less than b means what? Yeah, the radius of the cylindrical wire is b, so r less than b means inside the cylindrical wire, right? Okay, okay. where where r is the radial distance, okay. Then they are asking the value of h for what? For r less than b is, okay. Here they have given the options. Option a, they have given as ZA by 3 R cube, and option B they have given as ZA by 4 R power 4. Option C they have given ZA R cube, and option D they have given as ZA R power 4 divided by what? Divided by 5. So these are the options they have given. So what is the question they are asking here? So they are saying that a long cylindrical conducting wire of radius B is placed on z-axis. A long cylindrical conducting wire is placed on z-axis, and it is carrying a current density, that is Z bar, is equivalent to what? Is equivalent to ZA into R cube, ampere per meter square here. The units of this one is ampere per meter square, right? Okay. The Z bar, that is Z into R cube, AZ cap, for what? For R less than B, where R is the radial distance here, where R is the radial distance. So then they are asking the value of H for R less than B. So that means inside the cylindrical wire, we have to determine the H field, right? Okay. Okay. So we know from Ampere's law. We know from Ampere's law. We know that from Ampere's law. Here writing the solution here. Okay. So from Ampere's law, so I can write a circulation of H field around any closed loop is equivalent to what? Is equivalent to double integral Z bar dot what? Dot dA bar. Right. So this is from Ampere's law. Okay. Okay. So now see here what they are saying here. They are saying that there is a cylindrical wire. There is a cylindrical wire. Okay. So a long cylindrical wire here. Let us consider this as the long cylindrical wire. Okay. So it will extend up to infinity, and here also it will extend up to infinity. So let us consider it is placed along what? It is placed along z-axis, right? And the current density Z bar is flowing along what? Current density Z bar is flowing along Z direction, right? And this Z bar they have given as what? ZA into R cube or something they have given, right? ZA into R cube. Okay, that's what they have given, right? Yeah. So the radius of this one, the radius of this cylindrical wire is what here? The radius of this one is how much? It is nothing but B. Okay, so they are asking us to determine the H field inside the cylindrical wire, So let us consider some point here, which is inside the cylindrical wire. Now I want to determine the H field at this location here. So for that, what I have to do with this radius here, let us say this radius is R. Okay, so with this radius, I have to enclose the current distribution with what? With a circular loop. See, we have already done this type of analysis in my lectures here. If you observe or if you listen my lectures, it is all these questions you can easily answer. Okay, the radius of this loop is nothing but what? R, right? Okay, okay. So the circulation of the vector field, the circulation of the field H field, the circulation of H field around this closed loop, the circulation of H field around this closed loop is equivalent to what? Is equivalent to the current that is penetrating through this loop, or the current that is penetrating through this surface. Understood? Okay. So what are the variables on this surface here? So if I consider a small differential area dA, okay. So if I consider a small differential area dA. So what are the variables here? So on the circular surface, what are the variables? Variables are nothing but R and phi. So what is the differential differential length along R is nothing but dr. What is the differential length along phi is nothing but what? R d phi. So differential area is nothing but r dr d phi. So dA bar is nothing but what? If you draw the unit normal to this surface, it is going to point in az cap direction. So this dA bar, we can write it as what? R into dr d phi az cap. So if you are my student, then you don't find any difficulty in writing this dA bar and all these things, right? So dA bar is nothing but r dr d phi az cap, and we know z bar, right? So this is equivalent to, so double integral. So z bar is nothing but what? Z bar is nothing but za into r cube. It is pointing in az cap direction. Dot dA bar is nothing but what? R into dr d phi az cap. Okay, okay. So that is the circulation of H field around this closed loop, right? Okay. So now see here, the magnetic field. The magnetic field is in which direction here? See, if the current is flowing in upward direction, the magnetic field is going to circulate in anti-clockwise direction. So the direction of H field is in which direction? It is in A phi cap direction. So I'm writing here closed loop line integral. So that is H is pointing in A phi cap direction. So dot, this is nothing but what? This is nothing but the differential arc length here. So if you consider a small differential arc length, so what you are going to get, the radius of this one is nothing but r. So the differential arc length, I can write it as what? R into d phi a phi cap. Okay, and we want to determine the circulation of H field around this total closed loop here. If you want to consider the total closed loop, you have to integrate this with respect to phi from where to where? From 0 to 2 pi. Okay, so this is equivalent to double integral. Here what are the integration variables? R and phi. So here you have to integrate with respect to r, and also you have to integrate with respect to phi. So here, since you have to consider this total surface, phi has to range from where to where? Phi has to range from 0 to 2 pi, right? So here you are having az cap, here you are having az cap. Az cap dot az cap will become 1. So you are going to get here za into r cube into r is nothing but r power 4 into what? Dr into what? d phi. So this is what you are going to get here. So now it is simple integration on both sides. If you do this one, you are going to get a H field intensity inside what? Inside the cylindrical wire. So what you are going to get here? A phi cap dot A phi cap is 1. So you are going to get a H into what? Integral H into R into d phi. So H is constant, R is constant. You can take it outside the integration. So you are going to have H into R into what? Integral phi equal to 0 to 2 pi into what? Into d phi. You are going to get d phi. So this is equivalent. This is equivalent to. So if I integrate with respect to r here, what you are going to get? You are going to get za into r power 5 divided by what? Divided by 5. Next, integrate with respect to phi. What you are going to get? You are going to get phi. SR integral d phi is nothing but phi. And if you substitute the range from 0 to 2 pi, you are going to get here 2 pi. Okay, so on LHS side, what you are going to get? H into R into integral d phi from 0 to 2 pi is nothing but what? 2 pi. This is equivalent to za into r power 5 divided by 5 into what? Into 2 pi. Okay, so this is what you are going to get. So now it is simple calculation to determine what? To determine H value. So what we can do? So here 2 pi, here 2 pi will get cancelled. So here 1 r and here 1 r will get cancelled. So therefore, so this 2 will also get cancelled here. 2 pi, 2 pi will get cancelled. Therefore, you are going to get H is equal to what? H is equal to za into r power 4 divided by what? 5 ampere per meter. So this is what you are going to get, right? So this is the H field inside what? Inside the cylindrical wire. So this is for R less than B. Okay, okay. Yeah. So this is the H field you are going to get. So now what is the right option for this question here? What is the right option for this question? So ZA R power 4 by 5. Okay, so that is option D. Option D is the right option for this question. ZA R power 4 by 5. Right? Okay, so I hope this question is also crystal clear. Okay. Okay, so I hope this is crystal clear. So with this, we have completed all the EMT questions for electrical students. So they have given 3 questions here. We have covered all those 3 questions. One is we have determined a triple integral divergence of E into what? Into dV. This is one question. And another question is based on curl of H bar is equivalent to what? Magnitude of Z bar. And another question is based on circulation of H field around any closed loop is equivalent to what? Double integral Z bar dot dA. Okay, so we have covered all these things here. You have covered all these things. If you would have studied Gauss law, then you would have solved easily this problem. And we know Ampere's law. We have dealt with Ampere's law also. If you know point form of Ampere's law, you would have answered this question. And if you know the integral form of Ampere's law, then you would have answered this question also. Okay, so this question is for 2 marks, and this question is also for 2 marks, and this question is for 1 marks. So overall you got for 5 marks, right? Okay, so I hope all these solutions are crystal clear, right? So with this I am ending up this EMT solutions, right? So all the best for all of you, and I hope all of you are going to get some good ranks, right? So all the best for your future also. So with this I'm winding up the session. So thank you for watching Entry app, and take care. Bye bye.